Thank you very much, everyone, for joining us today. We're excited to get this webinar started, particularly since we know there are so many users out there who are interested in this topic we'll be talking about today. Here we have a quick overview of some of the topics we'll be touching on today. And before we jump into it, just a reminder that you can privately submit questions via the webinar interface throughout the presentation, and we'll select several of them to answer at the end. We wanted to start off by looking at a broad overview of some exciting applications for high-performance 3D printed parts used in several industries. In the aerospace sector, there's a lot of interest surrounding high-performance thermoplastics. This may include anything from cabin interior applications, which are enabled by the flame, smoke, and toxicity characteristics offered by the polymers we'll be discussing today, composite layup applications, enabled by their extreme temperature resistance, and space applications, made possible by outgassing performance under vacuum. The automotive sector is equally, if not more, driven by time and cost savings, especially at scale. Naturally, for fused filament fabrication, FFF processes, this typically leads us towards tooling and rapid prototyping applications. Tooling in the form of jigs, fixtures, and general assembly aids remain a popular use case. High stiffness and high strength to weight polymers enable efficient end-of-arm tooling applications. Affordable engineering-grade polymers, which withstand under the hood temperatures, now also enable functional prototyping at a lower cost than ever before achievable. The biomedical space has some unique needs on the 3D printing side, such as requiring materials that can be subjected to autoclaving or sterilization by ethylene oxide, steam, or gamma rays, or requiring parts with sufficient mechanical strength to support a particular weight profile, while also being safe for skin contact, or even providing an effective scaffold for bone or tissue growth. We wanted to also mention the education space, since there are plenty of academic departments and research teams interested in additive manufacturing, covering many of the applications that we've mentioned so far, but with a particular focus on exploring parts printed from a wide variety of materials. This has led to the strong interest that we are seeing for open source or open materials platforms, like our ANM2, that offer users the option to print with any of the thousands of filaments available on the market. Furthermore, we've gone as far as helping universities install their own proprietary toolheads on our machines that they then use to develop their own intellectual property. So, what makes PEKK, PEKK, and ULTEM so special? If you signed up for this webinar, you've probably already heard that they're the strongest 3D printable thermoplastics on the market. And this is where I'd like to hand the presentation over to my colleague, Dr. Abraham Avalos. His doctoral research focused on polymer synthesis for biosensing applications, and he also has plenty of experience in polymers processing, characterization, and synthesis, and has participated in numerous projects on additive manufacturing of these high-end polymers for aerospace, automotive, and biomedical applications. Dr. Avalos.
Hi, everyone. Although there are a number of different versions of this pyramid that exists in the world, and there may be some debate about what plastics belong in the high-performance versus engineering categories, generally, this pyramid is used to separate thermoplastics based on their mechanical properties and chemical or temperature resistances. At the bottom are our consumer-grade polymers like ABS and PLA, followed by engineering-grade polymers like polycarbonate and nylon. High-performance polymers generally offer greater strength-to-weight ratio as well as higher continuous operating temperature than engineering-grade polymers. In order to completely explore the exciting world of printing high-performance thermoplastics, we need to briefly touch on some of the key differences that separate these materials in the 3D printing world. Some polymers, such as PEKK and PEKK, are semi-crystalline, whereas others, like polyethylamide, are amorphous. PEI or polyethylamide is more commonly referred to by SABIC's trademark name, in North America, ULTEM. To explore the differences between amorphous and semi-crystalline polymers, we need to understand the glass transition temperature, often referred to as TG. This is the temperature where a polymer changes from a rigid amorphous state to a more flexible, rubbery state. The glass transition temperature of a polymer defines its state at any particular temperature. For example, operating below the TG offers you the strength of rigidity. Operating near the glass transition temperature may offer flexibility. If you need to extrude a thermoplastic polymer, it would need to happen at the melting temperature or well above the glass transition temperature. Amorphous polymers do not exhibit a true melting point. They have a glass transition temperature where they begin to change from a glassy solid to a rubber-like state. Then, at higher temperatures, they change to a viscous fluid. The disordered structures of amorphous polymers leads them to transition to the fluid state over a temperature range rather than at a distinct temperature. When crystallized, semi-crystalline polymers contain both crystalline and amorphous structures. Unlike amorphous structures, crystals are arranged in ordered packed manner. Semicrystalline polymers exhibit both a Tg due to their amorphous phase and a melting point Tm due to their crystalline phase. Their melting temperature is when all the crystals have dissociated into individual polymer chains. Part of the mechanical strength, as well as the temperature and chemical resistances for semicrystalline polymers, come from crystallite formation. Crystallites are dense crystal packs that are held together by hydrogen and dipole interactions. When printing, crystallization rate is never constant and is largely impacted by the environment where the molten polymer is extruded. Remember that the printing environment has many temperatures affecting the crystallizing bed, the layer below it, the heated bed, the chamber temperature, the convective currents in the chamber, the temperature at the nozzle, and the layer dwell time. A quick change in temperature or a large temperature gradient between the extruding bed and the environment can result in overall low percentage of crystallization. Let's move on to talking about our three high-performance materials, PEKK, PEKK, and ULTEM. PEKK is a high-performance semicrystalline thermoplastic in the polyaryl ether ketone family with a glass transition of 143 Celsius and a melting point of 343 Celsius degrees. It offers excellent mechanical, and chemical resistance properties that are typically retained up to 240 Celsius degrees, although some grades have continuous operating temperatures up to 260. It's worth noting that processing conditions have a significant impact on these mechanical properties. PEKK also resists thermal degradation and is stable in organic and aqueous environments. It's one of the few plastics compatible with ultra-high vacuum applications, for example, as required by the aerospace industry, and also for biomedical applications due to the resistance of certain grades to different sterilization and autoclaving processes. It can be expensive, so it's typically selected for the most demanding applications or as a lightweight metal replacement option. We suggest using solvate's grade of PEKK filamentized directly from solvate. They are free from additives, which affect crystallization rates, and the material handling is top-notch. From the mylar vacuum bags to the metal spools to the well-controlled diameter tolerance. PEKK is another PEKK family member, but unlike PEKK, PEKK is a copolymer with a crystallization rate that can be tuned via the ratio of terephthaloyl and isophthaloyl. It has a slightly higher glass transition temperature of 160 Celsius, and the melting point is 305 Celsius degrees for its pseudomorphous grade, and a melting point of 332 Celsius degrees for its semi-crystalline grade. The pseudomorphous grade has such a slow crystallization kinetics that it can act like an amorphous polymer. PEKK is often recognized for its printability, which is due to its slow crystallization kinetics that are much easier to control than PEKK and can lead to better layer welding. It can be printed in conditions that cause it to produce either a semi-crystalline or an amorphous part. Arkema supplies base resin for PEKK, to Chemia, who provides some of the highest quality compounding and filamentization we've seen on the market. ULTEM 9085, the most frequently used formulation in 3D printing, is an amorphous polymer with a TG of 185 Celsius degrees. It offers low flammability and smoke emissions when exposed to flame, as well as low smoke toxicity. ULTEM also offers high strength to weight ratio, good dimensional stability, high impact resistance, and broad chemical resistances. SABIC, the trademark owner for the name ULTEM, is our preferred supplier. Users benefit from their exceptional diameter tolerance and access to material traceability reports.
Print success starts before you hit print and finishes long after the print run. Every one of the following steps is essential to consider, especially for high-performance thermoplastics. Many thermoplastics are hygroscopic, and humidity accumulation can significantly impact part aesthetics and can increase degradation at higher temperatures. It can accelerate the crystallization rate of some polymers, which may contribute to layer bonding issues and reduce overall mechanical strength of the part. In this table, you can see some of our recommended drying conditions for various polymers. We've left in other engineering and consumer-grade polymers for comparison. We won't spend too much time on this table, but generally, the best practices used for drying materials for injection molding should apply to 3D printing. When extruding, a 1.75 millimeter diameter thermoplastic filament is melted and extruded through a nozzle that is between 0.2 to 1.2 millimeters in our case, which causes the polymer chains to become constricted and organized to some degree. Depending on your part geometry, the material you're using, and the thermal conditions in your printer, you may need to tune your extruder print speed to ensure you achieve the desired final print quality, as well as feature resolution on your part. Process control is about much more than just your nozzle temperature, bed temperature, and chamber temperature. Anything that alters part quality and repeatability needs to be considered. For example, in a system with active chamber heating, the effects of forced convection across the part surfaces play a massive role in final part quality. Also, precise control over the melt zone impacts many things, including the responsiveness of your extruder's micro-retractions.
First layer adhesion is a topic that deserves its own webinar, and you can watch for one of those in the future, but it's key to understand the material of your build plate and its interaction with your printed material. Poor first layer adhesion can cause warping, whereas if the first layer is too strongly attached to the plate or the part may be damaged during removal. Generally, high bed temperature, print speed, layer height, and extrusion temperature all work together to create a successful first layer. It is well known that part strength along the vertical axis is the weakest of any of the directional axes for FFF parts. This is due to the challenge of promoting interlayer bonding along the z-axis. When a new layer is deposited on a previous layer, it also imparts some of its heat to the layer below. This creates a temperature interaction zone between the new layer being printed and the previous layer. Many variables affect this interlayer welding zone: the temperature of the extruder and the environment, the layer height, the layer width, and the travel speed of the tool head. For both amorphous and semi-crystalline materials, it's crucial that the environment where layer welding occurs is carefully controlled to ensure good part strength. Let's compare the layer welding zones for amorphous and semi-crystalline polymers. As a new layer is extruded on top of the end layer, it cools towards the environmental temperature, while also transferring heat to the end layer below it. This heat transfer softens the lower layer, improving polymer chain migration and interpenetration, which in turn are beneficial for improving layer welding. We recommend that amorphous polymers are printed at the highest possible chamber and bed temperature, keeping the bed temperature as close to the TG as possible to maintain a uniform temperature profile for the overall environment. Semi-crystalline polymers offer a unique challenge since crystallization leads to further shrinkage, which builds internal stress that may lead to deformation. Crystallization at a lower layer may prevent chain migration in the interlayer welding with the following layer. There are two approaches to print PEKK. Our system gives you access to both. First of all, you can cold print amorphous PEKK. This is where the part is quenched from the extrusion temperature to a colder chamber temperature, resulting in an amorphous print. Crystallization is achieved only in post-processing through the heated annealing process. This provides good layer welding, but there is a significant risk of deformation. The other method is in situ crystallization. A high chamber temperature and very high nozzle temperature promote in situ crystallization while the bead is laid down. This achieves acceptable layer welding without the need for any post-processing. Thermoplastics typically decrease in volume as they cool from molten to solid states. The environmental temperature, including the chamber and bed temperatures, have major impacts on how much the first layer shrinks as it is deposited. Each following layer that's deposited on a part will also go through the same cooling and shrinking process, creating residual stress that exists within the part and accumulates layer by layer. When the incremental stress that accumulates is large enough to exceed the attachment force to the bed or even the interlayer bond strength, the part will warp. Usually, this results in the edges of the part bending outwards, although it can show up in other ways as well.
Annealing is a post-print heating process used to relieve internal stress built up during printing and improve crystallization in semicrystalline polymers to generate stronger and more stable parts. Amorphous polymers can be annealed at any high temperature just below their TG. Above TG, the part can start to deform. For semicrystalline parts, the annealing can be done at temperatures above the TG but below the melting point to improve crystallization. Always dry parts using the same drying protocol recommended for the filament before you proceed to annealing. So now that you have a good idea of many of the factors involved in printing high-performance thermoplastics, how do you choose the right printer for the job? There are a number of components that are key to consider when looking at an industrial 3D printer for printing PEKK, PEKK, and ULTEM, not the least of which are the elements involved in managing the temperature of your key environments inside the printer, the hot ends, the build plate, and the chamber. For high-performance polymers, you will need a hot end that can reach and exceed the material's melting temperature in the case of semicrystalline polymers, or will reach well above the glass transition temperature for amorphous polymers. Look for printers that offer cooling systems, such as a liquid cooling loop, tied into the hot ends. These extend component lifetimes and also offer precision control over the filament softening profile within the hot end. The AEON M2 uses dual fully independent hot ends, which can reach temperatures higher than 500 Celsius, more than enough for printing PEKK, PEKK, and ULTEM. Since we know how important the build plate is to first layer adhesion, ensure you have a heated build plate that can reach suitable temperatures to enable the molten polymer to grab deeply into the cavities of the surface and also create good interaction between the two materials. In particular, when printing PEKK, the heat flowing from the build plate surface helps to accelerate the crystallization process. The AEON M2 offers a high-temperature build plate geared towards printing with PEKK, PEKK, and ULTEM that can reach temperatures above 200 Celsius. An enclosed chamber is essential for printing high-performance thermoplastics, but it should be noted that not all chamber heating is created equal. Pay attention to how heat is applied within the chamber. Are conditions isothermal? Is the rate of forced convection controllable? When you're considering acquiring an industrial 3D printer, ensure that it uses active chamber heating, meaning there is a mechanism for circulating the air in the chamber to ensure that it creates isothermal conditions throughout the print run. Some 3D printers offer chamber heating that lacks that active component, which results in uneven heat distribution and can create additional challenges for achieving high-quality prints. The AEON M2 has an actively heated build chamber and can reach 120 Celsius. The largest advantage of a secondary nozzle or extruder is the ability to seamlessly print breakaway or soluble support materials. Having a completely independent secondary nozzle on a toolhead assembly, rather than having it on a lift mechanism or sitting coplanar, minimizes the risk of nozzle-to-part collisions or molten filament dripping and oozing onto your part. The AEON M2 offers dual independent tool heads. When considering the parts you'll be looking to print, it's useful to be able to print more parts more ways. A larger build envelope offers the flexibility of printing large batches of smaller parts, as well as printing large tooling in one piece. Unlike other plastics that might lend themselves to post-processing techniques such as bonding that allow you to fit together smaller parts, PEKK, PEKK, and ULTEM parts offer some challenges in this arena, which is why it's incredibly useful to be able to print larger parts all together in one piece. At 18 by 18 by 25 inches, or 450 by 450 by 640 millimeters, the AEON M2's build chamber is massive. When looking at an industrial 3D printer, you should consider exploring its slicer, as well as any software used for controlling the machine. Some important questions to ask are, how accessible is the slicer, and will it cost you anything? Does the provider include machine-specific build profiles for key materials? Can I control the 3D printer remotely from a computer? Can I air gap my machine? At AEON 3D, our printers come with a license for the widely used slicer Simplify 3D, as well as build profiles for a wide range of materials from leading chemical companies, and a lifetime license for our proprietary software used for controlling the AEON M2. Our system is built for flexibility. While we suggest Simplify 3D, you can use raw G-code generated in MATLAB, or use Cura or any other open platform slicer. Customers also have the option of downloading firmware updates online or air gapping the printer for security purposes, and we'll ship you the updates for installation. A major consideration in the industrial 3D printing space is whether your system is an open or closed materials platform. Are you locked into using expensive proprietary materials and per material license fees, or are you free to unlock the thousands of filaments available on the open market? At AEON 3D, we are committed to an open materials ethos. We want to provide platforms that allow users to print with any filaments they choose, since new materials unlock new applications. This also drastically reduces operating costs by allowing users to buy from a competitive, rapidly commoditizing materials market that eliminates the risk of supply chain singularity. This comes with the built-in flexibility needed to develop your own processing parameters, which is essential if you're developing or working with your own materials. AEON 3D was founded by a team of materials engineers with a focus on improving accessibility to additive manufacturing with functional materials. 3D printing high-temperature thermoplastics and achieving high-quality parts requires expertise beyond what can be learned from printing PLA on a desktop system. This is why it's important to invest in a hardware original equipment manufacturer that is also geared up to be a solution provider, one who understands how polymer chemistry and process parameters impact final part properties. AEON 3D's team of application engineers is here to provide end-to-end training, material selection advice, build profiles and slice audits, as well as general applications expertise and support. Thank you very much for attending this webinar. If you're interested in taking your journey into 3D printing high-performance thermoplastics, please visit us at aeon3d.com, where you can request a free sample part or get in touch to book a meeting with one of our 3D printing experts. If you have any questions or have submitted any during the course of the presentation, we're going to answer a couple now, so please get yours in if you haven't contributed yet. And we're going to have our head of business development, Leif Tiltons, to step in and help answer some of your questions.